Okay, it's once again the clock is not working. I'm not sure why we can't get a clock to work in a science classroom, but it's not 10 o'clock. It's 11 o'clock and time to start. Two quick announcements. There is a new Bacon quiz available. It's on electrophilic aromatic substitutions, so feel free to use that as preparation for the regular exam or the final exam. Trent? Unfortunately, yes, you do. It's a semester by semester thing, and the person who runs it is a good friend of mine, and he assures me that they're not making any profit on it, that they're just using it to maintain their servers and so forth. But yes, you do have to pay separately for the second semester. Exam number one, of course, begins Wednesday, so there is a recorded review where we went over the key topics from chapters 16 through 19. So you should watch that review. It's posted on Learning Suite, posted on YouTube with the link on Learning Suite. And we're going to have an online question and answer session on Zoom at 7 o'clock tomorrow. I will send out the link for that by email later today. So make sure you look for that in your email and come on and ask questions of me. There is, of course, also the sample exam that you can work. I will post an answer key for that later today as well, but we'll give you plenty of time to work on that without the answer key. All right, today we've got one more topic to finish on electrophilic aromatic substitutions, reduction of nitro groups, and then we're going to go into chapter 19, carboxylic acids, with the typical introductory material that we have at the beginning of each chapter, followed by a discussion of the preparation of carboxylic acids and their reactivity. So the last reaction of chapter 18 we're looking at is the reduction of the nitro group. We told you that nitro groups are not commonly present in the products that organic chemists want to use as pharmaceuticals or consumer products, but amines are. We do not have a way of installing an amine directly via electrophilic aromatic substitution, but we can install nitro groups and we can reduce them to amines, and we have three sets of conditions that will do so. Hydrogen, palladium, carbon is probably the easiest, but if your molecule was complex and it had an alkene somewhere else in the molecule that would also react with hydrogen and palladium carbon, we have other ways of reducing just the nitro group without affecting the alkenes, and that would be using either iron or tin metal in conjunction with HCl. Of course, if your molecule had a functional group somewhere else that would react with the strong acid, then you would want to use the hydrogen or palladium carbon. Okay, so it's nice to have these different sets of reaction conditions. So as an example of how this would be applied, let's say that we need to make meta-bromoaniline. Do you see a problem with making this compound? And if so, what is it? Okay. I think I heard some murmurings of the correct answer out there. Anyone want to raise their hand and explain what's the problem with trying to make this compound? Yes. Okay, the groups are meta. What are the directing properties of the bromine? Orthopara. What about the amine? Exactly. We have two orthopara directors and we need them to be meta to each other. So the only way to do that is in our retrosynthesis to convert one of these two groups into a meta director. Okay. We just learned that we can reduce a nitro group to give an amine. So in the retrosynthetic direction, we can go backwards from an amine to a nitro group. Okay. What are the directing properties of our nitro group? Meta. Okay. So as we go back one more step, which of these two groups are we going to want to remove? We're going to want to remove the bromine and leave the meta director on the ring. And then if we had to start from benzene, we know that we could retrosynthetically disconnect that nitro group and make it back to benzene. Okay. So let's take a look at the synthesis in the forward direction. What are our reaction conditions to make nitrobenzene from benzene? What reagents do we need? Okay, we need nitric acid and sulfuric acid. Okay. All right, what do we do next? What's our next reaction? Okay, Grace? Okay, we need to brominate next. And we accomplish that with bromine and iron tribromide. Okay. As we mentioned, our nitro group is a meta director. So that bromine is going to end up meta to the nitro group. Okay. Now we need to reduce the nitro group. And we would have three choices. Let's go ahead and use iron and HCl in this case. It wouldn't matter in this particular case. And that should say NH2. Okay? Question? Okay, the nitro group is a strong deactivator. Which of our electrophilic aromatic substitutions does it prevent? It prevents the Friedel-Crafts reaction. So we would not be able to perform a Friedel-Crafts acylation or alkylation, but we could perform any of our other three reactions. We can perform a halogenation, we can perform a sulfonation, and we could perform another nitration if we needed another nitro group. Okay, so it's only the Friedel-Crafts reactions that are prevented by the nitro group. Good question. All right, what if we needed the halogen ortho to the amine? Could we modify this sequence and end up with the halogen ortho to the amine? Any ideas? Yes. Exactly. If we switch the order of the nitro reduction and the bromination, we would convert that meta-directing nitro group into an ortho-para-directing amine. Okay? So if we needed ortho-bromoaniline, we would just switch the order of these steps. Of course, we would be doing the bromination of a highly activated benzene ring, so we'd need to leave out our Lewis acid if we wanted the monobrominated product. But we would be able to get it. Okay? So the timing of the switch from a meta-director to an ortho-para-director in your synthesis would be dictated by the relative positions of the substituents. Okay? All right, let's look at tri-substituted benzenes. So far, we've looked at how we would make a di-substituted benzene, but you might have to make a tri-substituted benzene on your exam, so let's make sure that we've practiced it. Okay. Yeah, I have no problem with letting you know the types of problems you're going to see on the exam. You don't need to have surprises. It's challenging enough without surprises. So, all right, we have a tri-substituted benzene here, and in my opinion, the best strategy for designing a synthesis of a tri-substituted benzene is to look at each of the three di-substituted benzene precursors to this and see if they're all viable. Would all of those be useful and able to be precursors for this compound, or would some of them not be possible? So let's start out. Let's disconnect our ketone. And we end up with ortho-nitropropylbenzene. Could we make this compound from ortho-nitropropylbenzene? No, why not? What would be the problem? Yes? That's exactly right. To attach the ketone or the acetyl group, we would need to perform a Friedel-Crafts acylation. We cannot perform Friedel-Crafts reactions with strongly deactivated benzenes. We've got a nitro group here. You might think, well, we do have this alkyl group. That's an activating group. That can counteract the nitro group. That's a weak activating group. That's our weakest activating group. And so it's not going to make the reaction possible. Okay, so Friedel-Crafts acylation will not work in this case. Okay, let's disconnect the propyl group. Is this disubstituted benzene a viable precursor to the desired product? Okay. I see people shaking their heads. No, why not? Okay. Okay, these are meta-directors, so we're not going to be able to put a group ortho to the nitro or para to the acetyl group. Okay, so that's one problem. That will prevent it. There's another problem that prevents it as well. What reaction would we need to install this group? We need a Friedel-Crafts reaction. Could we do a Friedel-Crafts reaction with two strong deactivators? We definitely could not. There's no way we could do a Friedel-Crafts with this compound. So that doesn't work either. So we better hope that our last choice is going to allow us to make this compound. So we disconnect the nitro group. Okay. Could we use this disubstituted benzene as a precursor to our desired product? Okay, yes. So we're performing a nitration. Do we have any restrictions on nitrations in terms of deactivating groups? The answer is no, right? Nitrations are not prevented by having deactivating groups on the ring in the same way that Friedel-Crafts reactions are. So we could perform a nitration. Let's look at the directing effects. In a disubstituted benzene, so on this particular disubstituted benzene, which of those two groups is going to control the regioselectivity or control the location of the third substitution? Which group? Alkyl group or the acyl group? The alkyl group, right? When we have two groups, we go with the stronger activator. This is an activator, that's a deactivator. So we know this is going to control it. Which carbon is this group going to direct the substitution to? The ortho, okay? It's an ortho-para director. Para is blocked, so it's only going to go ortho. There's symmetry here, so these two ortho positions are the same. So we'd only get one product, and it would be this one. This group is subservient to that one, but it is a meta-director, so actually its directing effects reinforce. So we're definitely going to end up with the nitro group in the right place. Okay, so we know this will work. Let's go ahead and draw a retrosynthesis. We know we're going to disconnect the nitro group first. Okay. Which group are we going to disconnect next? Propyl or acetyl? Acetyl, why? Okay, it's a deactivator, so that's a good reason to take it off. What's the relationship between these two groups? They're para. What's the directing effect of the propyl group? Orthopara. What's the directing effect of the acetyl group? Meta. Okay, so we need to disconnect the meta director and leave the orthopara director if we want the para product. Okay. So you see how important it is to understand those directing effects when we're designing a synthesis of a substituted benzene. All right, propylbenzene, can we make that directly from benzene itself? The answer is no. Why not? Yes. It would rearrange. If you try to attach a primary alkyl group longer than ethyl by Friedel-Crafts alkylation, you get a rearrangement. So what's the solution? What's going to be our precursor to the propylbenzene? You don't have to name it by IUPAC if you can just describe it. Yeah, it'll be the ketone, because we know that we can reduce the ketone to give the alkyl group. And then we can disconnect the acyl group by a Friedel-Crafts acylation to get us back to benzene. Okay, let's design our synthesis now. What reagents do we use in a Friedel-Crafts acylation? You don't have to use IUPAC names, just general terms will be fine. What do we call the compound we use in a Friedel-Crafts acylation? Okay, we use aluminum trichloride, AlCl3. What do we call this type of compound here? It's an acid chloride. Okay, so we're going to use an acid chloride and aluminum trichloride. Okay. Now, if we look at our retrosynthesis, the next thing we need to do is reduce that ketone to give us our propyl group. What reagents could we use for that? You'll obviously want to have these reactions at your fingertips before you go into the testing center. Sounds like we've got some work to do before then. What conditions? Yes? Okay, so that would work. That would reduce this to an alcohol, but we need to reduce it all the way to a CH2 group. So we learned a reaction last week that will reduce it to a CH2 group. Okay, zinc. You can use zinc and mercury. When we write it like this, that means it's an amalgam of zinc and mercury. It's not like a stoichiometric sigma bonded material, but we have this zinc mercury amalgam, and we have HCl. That's known as the Clemmensen reduction. The other conditions are the Wolff-Kishner reduction, which would be hydrazine and hydroxide. Either of those will work. Now we have our propyl group on. What are we going to do next? Look at our retrosynthesis. What comes next? Friedel-Crafts acylation. We already have the conditions for that. We just need a different acid chloride in this case. So we need acetyl chloride, aluminum trichloride, Is this the only product we get? What else do we form? We form the orthoisomer. And in electrophilic aromatic substitutions, anytime you form two isomers, you need to acknowledge that if you're writing out a synthesis. Even if you only want one, you need to acknowledge that you know that you're going to form a second isomer and that you're going to need to separate that second isomer. In the lab, you'd probably be able to use chromatography to separate it. Okay? But make sure you let us know you're aware that two isomers are going to be formed whenever that is the case. Okay? All right, what's our last step? Nitration. We've got that. We use that in our other synthesis over here. So we've already got that on the board. Nitric acid and sulfuric acid. Okay? So to successfully execute a multi-step synthesis, ending in a tri-substituted benzene, you've got to be very familiar with the activating, deactivating effects, the directing effects, and the reaction conditions. You've got to have those reaction conditions at your fingertips. As we learned last semester, making flashcards is a good way to learn those reagents, those reaction conditions. So make sure that you study those before the exam. Any questions about synthesizing tri-substituted benzenes? All right, let's go on. Let's turn the page to chapter 19, where we're going to talk about carboxylic acids. So we studied acid-base chemistry way back in chapter 2. This chapter is going to be a bit of a review of acid-base chemistry. It's situated at this point in the class because the next section, the next several chapters, deal with the reactions of carbonyl groups. And those reactions involve a lot of acid-base chemistry. So we have to understand acid-base chemistry well in order to understand the reactions of carbonyl groups. So we have a chapter here in the book that allows us to review acid-base chemistry, as well as to focus on carboxylic acids, which are the most common organic acids, the acids that we'll see most frequently in organic chemistry. So let's look at the structure of carboxylic acids. And this group, a carbonyl group with an OH attached to it, is referred to as a carboxy group. So anytime we have a carboxy group attached to an alkyl group or an aryl group, we have a carboxylic acid. We have 3 polar bonds in a carboxylic acid. We have these 2 oxygens, and the 3 bonds to those oxygens are all polarized towards the oxygens. So if we look at this electrostatic potential map of acetic acid, one of our simplest carboxylic acids, we see red on the oxygens and partial negative charges on the oxygens. We see blue and partial positive charges on the carbonyl carbon and the OH hydrogen. Okay, and that's what we would expect based on the polarity of these bonds. Okay. One other interesting feature of the structure of carboxylic acids is related to the bond length of the carbon-oxygen sigma bond. Okay. So this sigma bond in acetic acid is 1.36 angstroms in length. For comparison, the corresponding sigma bond in methanol is a little bit longer, 1.43 angstroms in length. Okay? Why is the sigma bond in acetic acid shorter than the sigma bond in methanol? Yes, go ahead. Okay, this carbon's sp2 hybridized. The carbon in methanol is sp3 hybridized. And when we form bonds with hybrid orbitals that have higher percent S character, the bonds are a little bit shorter. And why is that? A little bit more challenging than the first question I asked you. Yes, go ahead. Exactly. So an s orbital is closer to the nucleus than a p orbital. So if your hybrid orbital has higher percent S character, then that orbital and the electrons in it will be closer to the nucleus, more attracted more strongly to the nucleus, and that leads to a shorter bond. Okay, so that higher percent S character, that orbital being closer to the nucleus, results in a slightly shorter carbon-oxygen sigma bond in acetic acid than what we have in methanol. Okay, very good. All right, so let's talk about nomenclature, our favorite subject. We'll spend a little bit of time on the nomenclature of carboxylic acids. So there's 3 key points in regards to the nomenclature of carboxylic acids. So for acyclic carboxylic acids, we need to first find the longest chain containing the carboxy group. The carboxy group has to be, sorry, I can't spell that. It has to be part of our chain. And then there's a parent name for that longest chain. We're going to drop the E off of that parent name. And then we're going to add oic acid. Okay? So our suffix for carboxylic acids is going to be oic acid. Second point, the carbonyl carbon of that carboxy group is always going to be C1. So you're always going to number that chain. It's always going to be at one end or the other. And you're always going to number that chain with the carbonyl carbon being C1. We can also have cyclic carboxylic acids. We cannot have a carboxylic acid in a ring because we only have one thing attached to it. But we can have a carboxylic acid coming off of a ring. And when we have that, so if our carboxy group is attached to the ring, then we have a different suffix, okay? So then we're going to add carboxylic acid as our suffix, okay? We're not going to drop the E. We're going to keep the E in the name because we have a consonant here at the start of our suffix, and it's going to be carboxylic acid. And as you might have imagined, C1 is going to be our point of attachment. Okay, that new group is going to be at C1 of the ring. So let's look at a couple simple examples to make sure we understand this. All right. How many carbons in our longest chain containing the carboxylic acid? 6. So what's the parent name? Hexanoic acid. Drop the E from hexane, add oic acid, hexanoic acid. What goes in front of the hexanoic acid? 4,5-dimethyl. Okay. All right. Let's look at an example of a cyclic carboxylic acid. All right. What's the parent name? What kind of a ring do we have? Cyclohexane. What do we put on the end? Okay. So we're going to have carboxylic acid. Then we have cyclohexane. What goes in front of cyclohexane? Okay, I heard a 2,5,5 trimethyl. Very good. Okay. So why did we have 2,5,5 instead of 3,3,6? Who would like to explain? Yes? Okay, so it's the lowest number to the first substituent. That's what matters, the first point of difference rule. And so if we go clockwise, we get our first substituent other than the carboxylic acid at carbon 2. If we went counterclockwise, it would be at carbon 3. Okay, so first point of difference rule, 2,5,5 trimethyl cyclohexane carboxylic acid. Any questions on our IUPAC nomenclature? All right, let's move on. There are lots of common names that are used in carboxylic acids. These common names have been around long before the IUPAC nomenclature. So these are well accepted. Carbon 1, C1 through C6 carboxylic acids. And you'll notice those names all end in ic acid. So if you have a name ending in oic acid, that's usually an IUPAC name. If you have a name ending in ic acid, that's usually a common name. Although caproic acid, because the parent name in the common system does end in an O, we do end up with oic acid. You also notice that if you have a carboxy group attached to a benzene ring, that's known as benzoic acid. So this is another common name similar to aniline, phenol, and toluene. So it's a fourth common name that you need to understand for substituted benzenes. Benzoic acid can be used as a common parent name for naming substituted benzenes. Okay. You also see Greek letters used frequently with naming carboxylic acids with the common names. So this would be the alpha carbon, this would be the beta carbon, this would be the gamma carbon. Which one is the omega carbon? We talked about this last semester. We talked about omega-3 fatty acids. Do you remember which carbon is omega? It is the last one in the chain. So anytime you use omega, it's always going to be the one furthest away from the carboxylic acid. So an omega-3 fatty acid has a double bond 3 carbons away from the last carbon in the chain. Okay. Dicarboxylic acids would have dioic acid in the name. And so, but the ones that we'll see in class all have common names. So this would be ethane dioic acid, but it's always referred to as oxalic acid. Oxalic acid is part of spinach, present in spinach. It's toxic, but you'd have to eat about 9 pounds of spinach in order for it to be fatal. I don't know anyone who can eat 9 pounds of spinach, so you don't need to worry about that. And we have another one, malonic acid. We'll see this later on in the class. Esters of malonic acid have important properties. And then there's another one that is common enough that it has common names that are in use, and that is succinic acid. Okay. And then our carboxylic acids, they are acidic, of course, and we can deprotonate them with a base, and we end up with a carboxylate group, the conjugate base of a carboxylic acid. And there's usually a counterion that comes with the base that did the deprotonating, so we end up with a salt. We usually end up with carboxylate salts. And this is how we would name those species. The cation always comes first. If we're using the common names for the carboxylic acid, we drop the ic acid and add 8. If we're using the IUPAC names, the way they've drawn it here, they're dropping the oic acid and adding O8, but you could just drop the ic acid and add 8. The same thing here, you just end up with that O stuck in the name. So when it's O8, it's coming from the IUPAC name. When it's 8, it's coming from the common name. Most of you have heard of acetate before. This is how that name is derived. Any questions? All right, let's talk about some common before we get to the common carboxylic acids, we need to talk about spectroscopy. Spectroscopy of carboxylic acids. Let's look at, and actually, let me back up. I'm really trying to get ahead of myself. We need to talk about physical properties of carboxylic acids. What kind of intermolecular attractive forces do we have with carboxylic acids, with 2 molecules of carboxylic acids? How can they associate with each other? Hydrogen bonds, yes. Not just any hydrogen bonds. Carboxylic acids can actually form the strongest hydrogen bonds of any type of compound. And actually, I need to draw this a little bit different to show this properly. So here's 1 molecule of acetic acid. We can have that form a hydrogen bond to the carbonyl of a second molecule of acetic acid. Okay. And it can form a second hydrogen bond to the same molecule of acetic acid, like so. All right? So we have these hydrogen bonded dimers with carboxylic acids. And these are the strongest types of intermolecular attractive forces that we're learning about in the class. So it stands to reason that carboxylic acids will have the highest boiling points of any compounds that we're going to study. And this table shows us that. All four of these compounds have very similar molecular weights. Boiling points vary depending on the types of intermolecular forces. Both an alcohol and a carboxylic acid can engage in hydrogen bonding, but we see that the carboxylic acid has a significantly higher boiling point due to this ability to dimerize. Okay? So hydrogen bonded dimers lead to highest boiling points of any class of compound in organic chemistry. Would we expect carboxylic acids to be water soluble? Yes or no? To a certain extent. To what extent? Yes, if we have 5 carbons or less, then those carboxylic acids will be water soluble. If the chain is 6 carbons or longer, that chain is too long to dissolve in water, too hydrophobic, as they would say in biochemistry. And so that is going to be what we would refer to as a fatty acid. Those long chain acids that don't dissolve in water are fatty acids, and they are important in biochemistry. We've talked about them a little bit previously, saturated versus unsaturated fatty acids. Okay, any questions about physical properties of carboxylic acids? All right, now let's go on to spectroscopy. Here is an IR spectrum of butanoic acid. We see 2 key features. First, we have the sharp carbonyl peak at 1700, the CO stretch. And then we have an OH stretch, which we know is broad and above 3000. With carboxylic acids, it's extra broad and massive. Usually it obscures about 1,000 wave numbers in range from about 2500 to 3500. The extra width of this OH peak in carboxylic acids is due to this high degree of hydrogen bonding. The more hydrogen bonding you have, the broader that peak is going to be. With carboxylic acids having these special hydrogen bonds, we get very fat peaks. Okay? Let's look at the proton NMR. First feature we see in the proton NMR of this one's propanoic acid is the OH proton is highly deshielded. It shows up between 10 and 12 ppm, the highest chemical shift of any proton in proton NMR. Why? Why is the proton of an OH group so strongly deshielded? Okay, we've got 2 oxygens. We look at our structure up here. So we know it's going to be deshielded because that bond is polarized towards the oxygen. And then we could say that this oxygen inductively could be deshielding it. Okay, so that plays a role. That's probably not enough to account for the chemical shift being in the 10 to 12 range, though. So if we want to account for that, for the extreme deshielding, we have to consider the impact of hydrogen bonding. Now, if you look at the hydrogen bond, initially you probably think that's going to be a shielding effect because we're bringing the electrons of the carbonyl group closer to the proton. That's going to shield it. But we have to recognize there's only so much attractive power to electrons that one proton has. So if you start to form a hydrogen bond to the proton, you're going to lengthen the sigma bond that that proton is forming to the other oxygen. So we form this hydrogen bond, that causes this OH bond to lengthen. And that lengthening of the sigma bond brings it further away from the oxygen and has a net deshielding effect. Okay? So hydrogen bonding has a net deshielding effect on the protons that are involved. And that's why we end up with this massive deshielding, because we have massive hydrogen bonding with carboxylic acids. Okay? And then we also see a small deshielding effect of the alpha hydrogens. Those alpha hydrogens are next to a carbonyl carbon that has that partial positive charge. So it is inductively deshielded, similar to how an allylic carbon, allylic hydrogens would be. So you see those hydrogens, alpha to a carboxylic acid, usually show up between 2 and 2.5 ppm. Okay. Then in the C13, as we would expect, the carbonyl carbon is highly deshielded. We've got the polarity of the bond. We've also got the circulating pi electrons there. So those usually show up at about 180 to 190 ppm. Okay. Any questions about NMR spectroscopy of carboxylic acids? All right, let's talk about interesting carboxylic acids. Here we have some common carboxylic acids. They have common names. Something else they have in common, if you look at this, the words on this slide, sour taste, bad taste, rancid butter, that doesn't sound very good. And terrible odors. We see things like dirty socks, locker rooms, body odor. This should also say vomit because it smells like vomit. Okay, carboxylic acids stink. Almost all of them stink. But the really cool thing and interesting thing is they stink differently. That means that our noses are sensitive enough detectors that we can detect the chain length of carboxylic acids because our noses smell these carboxylic acids differently. In a normal year, I would have samples of C2 through C5 carboxylic acids, and I would invite those of you brave enough, it would be an optional activity because some of you would get nauseated, but I would invite those of you brave enough to come up and smell them and actually notice that you could detect the difference between a single CH2 group in the chain of a carboxylic acid. We're not doing that this year because we don't want you congregating, smelling the same bottles. That would be problematic. So you'll have to take my word for it, unfortunately. Okay. Butyric acid or butanoic acid is particularly bad, and it has actually been used as, I guess, a bioterror weapon, if you may. There have been extremist groups that have dumped butyric acid in various locations. Anti-whaling activists have dumped it on whaling ships, rendering them, people can't work if they're going to puke all the time, so that doesn't work. Anti-abortion activists have dumped butyric acid in abortion clinics. And whether or not you agree with the causes that these groups are trying to promote, doing this is actually a felony because the amount of damage that it causes. If you get butyric acid on a carpet, you have to replace the carpet, and you end up with a lot of damage. So don't try this, regardless of whether or not you sympathize with any of the groups that have used butyric acid as a bioterror weapon. Okay, it really, really stinks. Trust me. Another interesting carboxylic acid is aspirin. This is one that we studied a bit last semester. It is a painkiller derived from salicin is the compound from nature. We can oxidize and hydrolyze it to get to salicylic acid. And Felix Hoffman at Bayer discovered that if you make this ester from the alcohol, you have a painkiller that has less side effects than salicylic acid. Okay? The mode of action of aspirin was unknown for 70 years or so. In 1971, so 50 years ago, John Vane, a British chemist, determined the mode of action of aspirin. And for this discovery, this very important discovery, he won the Nobel Prize in 1982. He found that aspirin inhibits the action of the cyclooxygenase enzyme, which is part of the pathway to produce prostaglandins. Prostaglandins are molecules that are involved in mediating pain and inflammation pathways. So if you inhibit their synthesis, you're going to reduce pain and inflammation. However, aspirin has side effects. There are other prostaglandins that protect the lining of your stomach. And so if you're reducing the biosynthesis of prostaglandins, you're also going to make yourself more susceptible to ulcers. And that is indeed a side effect of heavy aspirin usage. So we fast forward to 1991, and there was a key discovery made here at BYU. Professor Dan Simmons a BYU biochemist, discovered that there are two forms of the COX enzyme. There's COX-1, which is involved in biosynthesizing the prostaglandins that line the stomach. And then there's COX-2, which is involved in biosynthesizing the prostaglandins involved in pain and inflammation. This same discovery was made concurrently by scientists at Rochester University. This was a hot area of research at the time. But the implications of this discovery are very clear. If you can design a molecule that selectively inhibits COX-2 and not COX-1, you're going to have a really good painkiller that reduces inflammation as well, and you're not going to have those same side effects on the stomach. They also found that aspirin inhibits COX-1 more effectively than it inhibits COX-2. Right? It's better at shutting off the wrong prostaglandin synthesis. So in the 1990s, every pharmaceutical company in the world practically was designing selective COX-2 inhibitors. They looked at computer models of the two enzymes to look at the active sites, to come up with hypotheses of what the active sites would look like, and designed molecules that they believed would bind selectively to the active site of COX-2, but not COX-1. And you'll see some similarities in the three molecules that made it to the market. They have a heterocyclic ring flanked by two aromatic rings, okay? And they have some different functional groups. These compounds came on the market in the late 90s and the early 2000s, but there was another complication. It was also found that there are some prostaglandins that are involved with the function of your heart muscle, okay? And so if you inhibit prostaglandin synthesis, you can also affect the function of your heart. And it turns out that Vioxx and Bextra have some significant side effects related to your heart. And so those were removed from the market due to problems that arose. Celebrex also has those side effects, but for a smaller population of patients. And so for many patients who have arthritis or other issues with severe pain, Celebrex is actually a viable drug, okay? Interestingly enough, Celebrex is produced by Pfizer. This is a company that everybody's heard of today, but Pfizer does more than just make COVID vaccines. They're one of the world's largest pharmaceutical companies. The research producing Celebrex originated at Monsanto, which is an agricultural products company, but used to have a pharmaceutical division that they sold and then was sold again and ultimately ended up with Pfizer. Dan Simmons had a collaboration with Monsanto that ultimately resulted in the production of Celebrex. Without going into a lot of details, Pfizer ripped him off and ripped off BYU, and they shut him out. Okay? But fortunately, we discovered what happened, and there was a lawsuit. It went on for years. Many lawyers made a lot of money. And the net result was that there was a settlement that was in the hundreds of millions of dollars. It was not published exactly how much money it was, but it was definitely in the hundreds of millions of dollars, split three ways between BYU, Dan Simmons, and the lawyers. Okay, so the Simmons Center for Cancer Research, I'm wearing my mask today from the Simmons Center, came out of that, some of the funds that support the Simmons Center. The prostaglandins do play a role in cancer. The COX enzyme has a role in cancer, so Dan Simmons was involved in cancer research as well as this painkiller research. And so that's why there's a cancer center established in his name. Okay. He's retired now from BYU. He can do whatever he pleases. He has enough money to sustain himself. And because of that, he's so passionate about research, he does research for fun now. Okay, so a very, very nice story. A very nice man, too. Very humble, very down-to-earth individual. I'm privileged to know him as one of my friends. Yes? With the heart? I don't. It's probably a very, very subtle structural effect that's difficult to explain, but I don't know the answer. Okay? So that's a great story. Has a happy ending for us here at BYU. But we need to move on. The last couple minutes, let's talk about how we would synthesize carboxylic acids. We've learned 3 ways to make carboxylic acids. Who can raise their hand and tell us one of them? Anyone? We learned one in our last chapter, so it should be fresh. What if we're going to make a benzoic acid derivative? What would we do? Either you're really shy or you've got a lot of studying to do before you take the exam. If we have an alkyl benzene that has at least one benzylic hydrogen, what reagent could we use to oxidize that to a carboxylic acid? Potassium permanganate, okay? So if we want to make a benzoic acid derivative, oxidation of an alkyl benzene will work, as long as there's at least one benzylic carbon-hydrogen bond. What if we have a primary alcohol? How can we oxidize that to a carboxylic acid? This goes back to last semester. Okay, I would suggest reviewing this. You can use potassium dichromate. You could use chromic acid, CrO3. You have a couple choices, but you have to use sulfuric acid and water. Okay. And then the third method, if you have an alkyne, you can perform an ozonolysis reaction of an alkyne, followed by addition of water. That makes a carboxylic acid. If you have a symmetrical alkyne, you would just get one carboxylic acid. If it was non-symmetrical, you would have two. So make sure you're familiar with these methods of synthesizing carboxylic acids. All right, last thing for today, reactivity of carboxylic acids. Of course, they're acidic, but they can also be basic. We'll talk about their acidity on Wednesday. But a carboxylic acid can actually be protonated by a strong acid. Which oxygen are we going to protonate? The carbonyl oxygen or the hydroxyl oxygen? Any ideas? The carbonyl oxygen, very good. As I'm drawing that, let's think about why you would protonate the carbonyl oxygen. Okay, so this is the conjugate acid we would end up with by protonating the carbonyl oxygen. What's special about that carboxylic acid, or that conjugate acid, sorry? What do we have here with this this conjugate acid? Okay, think back to your principles of resonance. All right, lone pair adjacent to a double bond. We can draw another resonance structure. These resonance structures are equivalent to each other, right? So we have the maximum amount of resonance stability, delocalization of that positive charge. We cannot draw those kinds of resonance structures if we protonate the sp3 oxygen, okay? So the sp2 oxygen will be more basic because we end up with a resonance stabilized conjugate acid. All right, we'll stop there. We'll talk about the acidity of carboxylic acids on Wednesday. Hopefully we'll see you on Tuesday in our Zoom review.